we're gonna, next Tuesday, we're done. I'm done. I'm going out of town like by Thursday. So if you want to take it early, that is possible. There's actually 2 people who've already talked to me are taking it early, and so I will have it ready. And so you can talk to me if you want to do that. Otherwise, we're taking it Tuesday. It's the same setup as every time. It's show your work. You'll have 3 hours. Yeah. And it is this question that Major always asks me. It is study set 10 through 14. So it is solutions, it is kinetics, it is radioactivity. So we just did the review for radioactivity. Go back and do your study sets and you'll do great. Kinetics is just a unique thing. Once you put the time in, you'll be great. So you might need office hours, some extra office hour time, and to not be shy about that. So today, get the radioactivity done, and do your topic. Focus on that. Get your paper done, whatever. I will have Saturday office hours. And so that's 10 a.m. because there's a group of people who always come to those. But I will have Monday evening. I can do an office hour because I'll be giving an exam then on Thursday. So Monday I'll have office hours from like 6 to 8. If you are in need of some extra help, I'll have an hour before on Tuesday. Thursday, I will have my regular office hour. So that is the time if there's some things you need to help you get going on the kinetics. The lab, again, for this weekend, it is all just math. It's good practice for the celebration. So I'm going to walk through these. I'm not going to necessarily, the answers are there. This is really good practice too. There's some things I want to point out with that. All right, I think everybody has given me a topic. Everybody has, so I'm very grateful for you. Yeah, considering last week at this time, I had 1 topic, so you guys came a long way in a week. You can absolutely change your topic. So I want you to do something that you're passionate about. Just talk to me tonight or send me an email and say, hey, I want to switch to this. Is that possible? And there's a couple of you I've emailed and said we have to refine that or be more specific. But and again, you can change up through Thursday. Presentations are either going to be at 3 o'clock or at 6 o'clock. And then I'll have an office hour from 5 to 6 in case you want to work on stuff. So once I get started on this, we'll take a small break. And if you have not told me when you're presenting, I will be calling your name out to find out when you are. All right. So kinetics, radioactivity is on there. We just spent 40 minutes on radioactivity. Kinetics, go back and redo the study sets and you've got this. So just a couple things to review. You will definitely have, we just did half-life. So I'm pretty sure you guys know how to do this. Biggest thing is stating the formula. If you are having trouble with half-life, and right, this is the natural log of the AT over A0 formula. There were 2 on today's study set. Please stay after today and say, hey, can we walk through this together? Because this is definitely on there. This is like we did it with kinetics, we did it with radioactivity. When you take Math 111, you work with this formula. It's one of the big uses of natural logs. And all right. And you will be asked, does it make sense? I know the other thing I wanted to mention with it, yeah, is K units. So I guess for all of you, I write comments to you on your worksheets. If there were issues. Some of you you can always have me look at it during office hours, but that would be one of the things, is people getting sloppy with units or showing their work. So you guys get this, you've had this whole bliss year of, right, being online school. Isn't this fun? And it's going to end, and you're going to have to go back to real school where you're going to be really, yeah. And so showing your work in physics, it's all about showing your work. So use this as a good time. Activation energy. Again, you guys have your notes nice and organized so you can go through this effectively. This is the natural log of K2 over K1. Couple things I wanted to point out with this one is the temperatures need to be in Kelvin. So just like when we did gas laws, and that's the other thing I wanted to point out, is the R. Again, 8.314 e to negative 3 kilojoules per mole Kelvin. So that is the R for using in kinetics. I mentioned that because our original R shows up on the next page. And so they both show up on the celebration. So in kinetics, we use the kilojoule R. This is just being able to plug into your calculator. So you'll state your formula, you'll plug everything in, and you'll get a number. You'll also have the question, does it make sense? So in the good old days when we were live in person, solving was worth more points. For you guys, doesn't make sense is something I'm really looking at that you can explain why it makes sense and how you can know. So I wanted to point out a couple of things, because solving you can do. The activation energy wouldn't be asked, does that make sense? It's more for question B. So if we increase the temperature, no, I'm sorry, we decreased the temperature. We were at 323 and 373. So sorry, my pens. If we decrease the temperature, what a lot of you wrote on your worksheet was we decrease the temperature, we decrease rate. And I wrote a comment to many of you last week. This is a week ago, so it's remembering this. And I said, you need a more complete explanation. So you may want to provide a more complete, this was actually a question that, why does temperature decrease rate?
Decreases the collisions.
Why does it decrease the collisions?
Decreases the kinetic energy. And
so this is the decrease in the giggles and jiggles. So a lower temperature means a lower kinetic energy, means you're going to have fewer collisions. There's two things happening here. You have fewer and less forceful on your collisions. We've talked about this with temperature. And so that decreases rate, which means you have a decreased K. The value of K is always proportional to the rate. There was a question on the study set. So as K goes down, it means it's slower. So a decreased rate is slower. Higher temperature, right? More giggles and jiggles, more collisions, more force of the collisions. The rate goes up, the K goes up. All right, so questions with that. And then this one I was talking about, you're going to do a rough estimate and say, okay, it looks like we went through more than 2 half-lives or not quite 3 half-lives. So you cut it in half however many times. All right, or there is one, I think the one on the worksheet, it went through like 8 half-lives. So basically nothing's going to be left. Mechanisms, I want to walk through this one because this is something. Oh, and the other thing is the charts. Sorry, so the chart, you know, where you're doing, you double it and it doubles, so it's first order. So just go back and practice those. I wasn't going to spend time because we've done that enough. If you're having trouble with the chart, that's going to be a one-on-one thing with me. So please don't be shy. Send me an email and say, hey, I need an office hour. because one-on-one will often not take us a lot of time, and just come to the office hour with the things you want to work on, or tell me beforehand. And again, I can actually even open up one. I have presentations tomorrow night at 6, but I can open office hour beforehand if you need that for just like a 20-minute like one-on-one to get you through a couple questions. With these, we're going to add the 2 equations up, and we're looking for the piece it's made in one reaction and used in the next one, and that's the intermediate, the N2O2. It might be used even 2 later, but it's not, it's something that is made but then used immediately. It's not stable. And then we add up what we have. So there's 2 No's and a hydrogen. And we get an N2O and an H2O. And we can check to make sure it's balanced. Looks good. The rate law is based on the slow step. So in this case, it was step 2. So rate equals K, you always show that little K. And then even though we crossed it out, it's there in the step. So N2O2 in hydrogen. I did one like this, I remember on Thursday. At where we're at in the class, you would just say that. This is not the correct rate law, because technically the intermediate can't be part of the rate law. But I haven't taught you how to get rid of the intermediate, so you would have to include it in the rate law. All right, so what this implies is the NO is 0 order. It's not part of the rate law. So if something's not in the rate law, it's just 0 order. All right, on C, the molecularity, there's 2 things colliding. So we're bye-bye. It's like you're on the airplane. Bye, bye-bye, bye. All right, in the energy diagram, I have to tell you if it's exo or endo, and it's exo. We're going to, let's go ahead and just sketch, or I'm going to sketch mine, ask you a question. So exo means you start high and you end low. So this is my reactants, the NOs, and then my products, the N2Os and the H2Os. All right, we're going to go up. Oh, I messed up, sorry. My first step is the fast step. So my first step really has no hump. It's like a little hump. And then my next step is going to have a large hill. So this is a quick comment for you all that this is, and it's okay if it's like a sloping hill. This would be like a special climb because it's got that negative slope thing going. So my first activation energy is much smaller because this is our fast step. This is very rare. Usually the first step is the slow step. And then from the intermediate spot there to the top of the hill, I have something underneath my papers. That would be my other EA2. So this would be called EA1 for the first step. And then EA2 is from that starting point. The difference from where you start to where you end, that is the delta H. So this was exo. So my question is, we can actually look at each step. So step 1, step 2, this is 2 steps, so we have 2 hills. Step 2 is exothermic because we're starting high and we're ending low. But if you look at how I drew step 1, I start you low and I end higher. So I actually showed step 1 as endothermic. And I mentioned this last week because I know on the celebration I specify every step. And so I'm looking for it to get even more detail. And then the catalyst is going to, it can't change these spaces in between, so the beginning, the end, and the space in between, but it is going to eliminate that huge hill. So it basically, there's my catalyst. lowers the activation energy. So it makes it go much faster. So that was a review of kinetics in under 10 minutes. Questions with that or anything? And again, you can email me. Go ahead, somebody's talking.
Yeah, just for the rate, the N2O2. Will you just go over that really quick? I think I just forgot it. Like how you got the rate again.
Slow. Whatever is your slow step, and that was step 2. It's almost always the first step. So whatever is your slow step, it's the reactance of the slow step. So the N2O2 and the hydrogen, we just put them in the brackets. Is that what you're okay, Major? Yeah, thank you for asking that. That's so you just take the slow step and you just put the reactants into brackets. You're multiplying them, so leave the plus out. Yeah, good question. Thank you. Anybody else questions? And then please do, like, we're writing rough notes on this, but please do go back and definitely do the math. And yeah. All right, it's 1 week. 1 week from now, 1 week in like an hour, 2 hours, we'll be done. All right, so the celebration does start with kinetics and radioactivity. That's half of it. And then we get solutions. So you can do solutions first, but I figured the kinetics and radioactivity are going to be fresh in your brain, and you're all going to get it. So if you get kinetics, that's like, okay, we got half of that done. So solutions, you guys all did good on it, but that was 2 weeks ago. And that Memorial Day weekend, my gosh, we had like the perfect Memorial Day weekend weather, and it wasn't hot, it wasn't cold. My mom in New Jersey, they had 3 inches of rain, they had 60 degrees. They desperately needed rain, but New Jersey was like, yeah, New Jersey Shore was not like the Bruce Springsteen song. Everybody goes to Jersey Shore for Memorial Day, and they all had to stay inside. They told me their sob story today, and I said, you needed rain. The plants are so happy. All right. The biggest thing with solutions, because again, you guys, you just have to have your notes nicely. So when we're going to walk through how to do these. The biggest issue is the assumption. And then it's just all formulas. And so I want to walk through how to make these assumptions. And the percent is easy. Percent, you're going to have 100 total. It's grams. So for percent, we're going to have 28 grams of the ammonia, which is NH3. And the total is 100, so plus 72 grams H2O. If I don't give you the solvent, it's water, that gives you 100 grams total. And it makes sense because percents, if you go back to 4th grade, when you learned about percents, they're out of 100. That's like what we did on the previous page. So like with these, when we do percents, we make the A0 100. It's the same idea there. So from that, you would just solve through it. I want to walk through these just briefly, and then I also want to talk about how to make an assumption if you started with some of the others. We did this in the notes, but solving for molarity, it's not just moles per liter. And if you write your formulas like that, you need to show your work beautifully. So it's the moles of the solutes, or moles of NH3 over liters of the solution, or liters total. So this is in some ways the hardest one, because you have to figure out your total volume. So this is where you'd have to use your 100 grams, and then our density has to be given. So this has to be our total mass, not just the water. And then you can change your milliliters to liters, blah, blah, blah. And then here we'd change our 28 grams, changing your grams to moles, blah, blah, blah. You guys know how to do that. Molality, this way I have to be careful, is the moles on top is the same. So moles of the NH3, and it's going to be over kilograms of just the water. So molality is different, and it's because of that. So on molarity, you need the total. We never actually care about the water. And on molality, we want solute and solvent. All right, that's why these can come out really different numbers. All right, mole fraction, that's the funky X. This is of the solute, so it's going to be moles of NH3 and then over total moles. So there's no, you just get a number. And so you just have to figure out your moles of each part. I'm trying to see if I have, I think, oh, it was on your worksheet. So, no, not in the worksheet. It was on the lab, the hydrophobia lab. It was the last page. So there's several of you who haven't turned that lab in, and you're going to get that into me. So labs are not optional. You have to do them. You guys are getting away with so much. Just do labs and get them in. But it was if you're given mole fraction. So, so this was on the lab, you were given that the mole fraction was 0.10. And it said, what do you assume? Oh, I know, it was of sucrose, like C12H22O11. So those of you who haven't done it yet, I'm giving you a huge hint of how to do it. Your assumption for mole fraction is that you have 1 mole total. So like here, you had 100 grams. Mole fractions, it's about mole. So you have 0.10 of the solute, which was the sugar, and then the rest, 0.90 moles, is, I didn't give you a solvent, so it's the water. And I would say everyone got it wrong, except the people who came to my office hour. And I will tell you, every one of them had it wrong until I had to correct them. And you all made the same wrong assumption. You all said, I have 1 kilogram of water. You did not have a kilogram of water. If you have molality, you have a kilogram of water. If you have mole fraction, that's what you're going to assume. So the assumption is you break it apart into the 2 pieces. You have whatever the number is of the top and then the bottom part. So we did some of these, but that should hopefully help you. This is not on this review, but it was on the lab on the hydrophobia. Any questions? This is just number crunching, and this, you don't have to do it tonight. Do it this weekend. Weather is going to cool down. Use your weekend, and then you can end, and we'll all be done. You'll end really strong. Boiling point and freezing point. Delta T equals K, to give you the K. The K is going to be given to you times molality, which you can write it like that, or you can say moles of the solute over kilograms of the solvent. And if it wants you to find molar mass, you're solving for moles. You're going to do this in 2 steps. So 1 step, and then your second step is you'll take the grams divided by the moles of the solute. So we did several like that. This is just another one. 2 things with this one. One is, well, a couple of things with all of these. We can write it down here. Units. Please show your units. And the other thing is Sig Figs. So we're going to try and respect Sig Figs here. The change in temperature is what's going to limit your Sig Figs. And so when you do the subtraction here, the temperature, it really gives you, it's always just an approximate, but it's good enough. And so that actually, the lab also has one of these on it. And then you can do a percent error with it. All right, osmotic pressure is just PV equals nRT. So you can change that to moles. You have to change this to liters. This has to be in liters. This is what we're going to solve for. That's going to be liters. That's our mole. Temperature has to be Kelvin. You have to change this to K. And then the R, I promised you 20 minutes ago. So this is the gas law R. 0.082057. That is ATM liter per mole K. This is for osmotic pressure. So be careful because there is also VP. So vapor pressure is a different formula. So this is where we just do pressure, different type of pressure, mole fraction. So the X means mole fraction, but this time it is a mole fraction of the solvent. Why is it the mole fraction of the solvent? Nobody knows.
Because of the I.
Oh, good. There is an I here. It's not because of the I, but thank you for pointing that out. The mole fraction is of the solvent because it's a solvent that is evaporating. So it is because the solvent evaporates. On the lab, they both evaporated. So then on the lab, you have to do X of the solute times P. This is the lab that half of you turned in, and there's still a handful of you, the hydrophobia lab. You actually have to do the solute also. So you have to figure out the solvent and its vapor pressure, and then the mole fraction of the solute and its vapor pressure. So I should take myself enough room. I is always multiplied by the moles of the solute. So on this one, the solute, you're not going to multiply the mole fraction by I. There's only one little piece of the mole fraction that will get multiplied by I. Here, the solute, the moles is right there. That's where you would, if there was an I, there wasn't on that one, that's where you'd multiply the I. And same here, we would multiply that by the I. So anywhere you see moles of the solute, that's where the I comes in. And so on this one with mole fraction, it's just where the moles of the solute, not the overall moles, shows up. Right, the other thing, and we'll take a break for a few minutes, but is you will have to, I didn't put it on here, but explaining why the answers make sense. So with vapor pressure, like freezing point we've talked about, it interferes with the pattern. And boiling point and vapor pressure, so as you add solute, you increase the IMFs, so less solvent escapes. We've done this before. We've written this explanation out many times. But again, it's been 2 weeks, and we always had this beautiful weekend, and now 1 week. You can all do it. Just take a deep breath. So less solvent escapes. So we'll see a decrease in the vapor pressure. So the vapor pressure is measuring how much escapes. In the case of boiling point, the boiling point goes up because you need more jiggles to make it escape because of the stronger attractions. All right, questions. I did that pretty kind of fast because the math, you've watched me do math for 10 weeks now. And so you just need to do the math. I'm looking for my last page. We're going to go over this page. I'm going to pause us. Don't take a break because I have to ask a bunch of you questions. Recording. All right. And again, I will on Tuesday I'll be here at 5. I can be here earlier. I can do an office hour earlier on Tuesday. So if you want an office hour on Wednesday, like 5 to 6, you have to email me. Or Monday, really, I can do Monday from 5 to 8 p.m. Again, you'll have to email me, and I can send you the link. Tomorrow, though, at 6 o'clock, that's why it's ending at 6, I have class presentations after that. Thursday this week, I will be in class presentations pretty much the whole day, but and Saturday I'll have an office hour. And again, if you want to take it early, just send me an email and we can figure that out because there's other people. But you want to figure out when your other exams are. So we're all taking it by Tuesday, though. All right. And this is just a reminder. So it's not just all going to be math and number crunching. There is going to be that page, the wall of words, something to avoid in your presentations. But yeah, and I do appreciate papers turned in before Sunday, but it's okay. You have till Sunday midnight to get your papers in your lab. All right, so if you filter and nothing remains, that rules out the suspension. So a suspension will leave, like salsa is a suspension. I think you all know what salsa is. So salsa will leave stuff. So it would leave residue on filter paper. Your voice is behind me, and so like teacher's gonna lose it in the last class, but the dog's not barking. The dog always barks when there's voices, so that's a little worrisome. The key for a colloid, which is what our answer is the light scatters. So an example of a colloid is fog. And so driving in fog, your headlights scatter. We don't get good fog here, but if you go to the Oregon coast, yeah. All right. Saturated and supersaturated. These are referring to solutions. And solutions have really tiny particles, so they're not going to scatter light. You can't filter them. It's difficult to separate them. But the difference between saturated and supersaturated is more question number 3. So the answer was C, and it's the scattering of the light that's the key there. If the light doesn't scatter, then it must mean that the solute is too small. And so then it would be that this guy is going to leave stuff behind on the filter paper, would have been our key there. It's just the terminology. That's like a 1-point question that I'm required to ask. All right. So you add a crystal and it just floats to the bottom. That means you're already max. You already have the max solute. And so that is a saturated solution. If it was unsaturated, then it would dissolve. Because you have room for more. If it was supersaturated, anybody know what would happen?
It would pull out
Yeah, it pulls out the extra.
the extra stuff.
So you would get a whole bunch of solute. You wouldn't just get that one that floats to the bottom. You'd pull out all the extra solute. So you'd have a whole bunch of solute coming out. So this example was saturated. All right, number 4, this has really been on every single one of our celebrations. So hydrophilic or hydrophobic. So carbon, hydrogen, we're looking for the one that's like it. So the C6H6. There is actually one more on this one. And this would take us back to the first celebration, which is, this is non-polar. It's carbon with 4 chlorines. This is non-polar or hydrophobic. So both of those would actually dissolve because this is non-polar. In the last test, we did it as if it was London or dipolar H bond. And this one, we're looking at it as far as solubility. And several of you will be moving on to organic chem next year. And that's actually one of the big points with organic chem. So the carbon hydrogen compounds versus these guys, once you get the hydrogen bonding, the A and D, ionic, those are going to be water soluble. They're going to be hydrophilic. All right. Gas, think of soda. We want high pressure and low temperature. It's not a gas law thing. It's just saying how to make it. So your soda, we like to keep it on ice. Oh, sorry. Oh, no, sorry. I'm reading on the screen and can't circle correctly. That's the hand-eye coordination that has not worked well for me. So a high pressure pushes the solute in, the low temperature, yeah, it's not jiggling it out. And so low temperature allows the solute and the solvent, yeah, to interact. And so it holds the gas in there. At high temperatures, it jiggles it and pushes it out. All right, if you add solute, which of these are going to increase? Well, boiling point increases and osmotic pressure increases because those are the two that go up. Freezing point and vapor pressure go down. And again, there's different reasons. The osmotic pressure is the solute pulls the solvent. So attracts or pulls the solvent across. So osmosis, again, is the movement of the solvent. So as you add more and more solute, you're going to cause more movement of the solvent. For freezing point, which went down, it's going to disrupt the pattern of the solvent. So solids are all about a pattern. There is one more here, which is concentration. So whether it was molarity or molality or mole fraction, as you add more, it's going to go up. These two, as you add the solute, you increase the IMFs. So less solvent escapes. We just went through that. Didn't give us much room, but so yeah, that explanation goes on. All right, number 7. You guys remember doing this a couple weeks ago? It's where we figure out the number of ions. So KCl is 2 ions. We gotta go somewhere over the rainbow. The osmo. So 0.08. I just put the os there because 2 things always affect it, the concentration and the number of particles. So every K and every chloride has a concentration of 0.04. Sodium phosphate, there are 4 ions. There are 3 sodiums, and then the polyatomic stays together. Yeah. So this would be 0.12 osmolarity. This is not ionic. So it just stays how it is. So it's just 0.10. So we don't have to multiply it. We just keep it how it is. In pure water, there's 0 solute. So it's our starting point. It is 0. So this is going to be my low boiling point. Sorry, I'm giggling because I see I want us to go from the lowest, the highest boiling point by numbering it 1 to 5, and there's only 4 choices. So apparently there used to be another choice. So that's our lowest. This is going to be our highest. So if we wanted to rank from lowest to highest, D is our low, and then A, and then C, and then B. It's going to be our high. I recommend that you label high and low, because what I find is some students like to go high to low, and some do it, what I said is go from low to high. And some of you just get it backwards. And all right. And you can make it as a list too, or as a row like that. All right, and then last one is, so we have our membrane. A is 2% sodium chloride, and B, we had some of these. Go back and look at your study sets also. And B is 10% sodium chloride. So osmosis is the solvent. The water moves to the higher, the water moves to the solute. So whatever side has the solute, the water is attracted to that side. So B has more solute. The ions do not move. So neither A or B is a choice. So it's the water moves from A to B. I have to personally myself, I have to make a diagram. But all right, initially A is lower because it's at 2%. When it gets done, they'll both be the same. And so that is hypotonic. So hypo means lower. All right, so if the water's moving, G is going to be correct. So the volume is going to actually increase. So we'll actually see that the volume will be different on the two sides. That's the idea of osmosis. It's quite fascinating, but and it's doing that because it wants the concentration to be the same. So the salt can't move. All right. So as the water moves to B, the concentration on side B will decrease until the two sides have the same concentration. So our choices were C, G, and I, or were the correct ones. A, since it's losing volume, it's going to become more and more concentrated. So just be careful. If you see a question like this, am I asking increase or decrease? And what am I asking, increase or decrease? So I went kind of fast, sorry. Because I'm motivated to be done like all of you. Is there any questions? For the good of the order. So last time I had to record. Thank you.